Welcome to AfterMath, the official podcast of the Math Citadel. I'm co-founder and research scientist Jason Athcock.
And I'm Dr. Rachel Traylor, co-founder and chief scientist.
This is episode 5, How to Annoy a Mathematician.
So we're going to discuss a few of our mathematical pet peeves, and a few, right? Because we obviously have more than 4.
Right. We may have to break this up into installments, similar to our brain wrinkles.
But that's okay. Some of these are light ones, and some of these are a little heavier. So, Jason, you want to go first?
Sure. Something that occurs frequently when you're talking to people that are interested in math, people that like to do math, people that are interested in sciences in general. I hear it a lot. They bring up use cases where they say, okay, I have a situation here, and I've looked at the math, I've done all these calculations, and I come up with this strange result, and they say, have I broken this theorem? A very famous theorem, like, okay, so have I broken the fundamental theorem of calculus? Or,
central limit theorem is the one I hear actually fairly common in data scientists. Oh, I broke the central limit theorem.
Right, okay. Fundamental problem with this language being used. A theorem cannot be broken.
Correct.
I just need to lay that out there. So if you think you've broken a theorem, you haven't.
So what you mean when you say you've broken a theorem is that the statement of the theorem does not apply to your situation. Now, the only way that you would even hypothetically be able to break a theorem is if you met the hypotheses of that theorem and then managed somehow to find that the conclusion of that theorem, despite meeting the hypotheses, is false. That's not breaking a theorem, that's simply finding a counterexample, and it means the theorem is now not true. So what is it that people really mean when they say they've broken a theorem?
Typically, it's born of, like, they didn't really read the big part of the implication at the start, the premise of the theorem.
Which actually ties into my little one, which is the central limit theorem isn't the answer to all of your statistical and data science problems. I have had people tell me that there are distributions or probabilistic situations that break the central limit theorem, and none of that is correct. What they mean to say is that the central limit theorem does not apply in their case. There are distributions for which if you draw a random variable and you take the random variable minus the mean divided by its standard deviation, that new random variable does not converge to a normally distributed random variable. However, none of those actually meet the hypotheses. What is the first hypothesis of the central limit theorem? And we do have an article on this, by the way, on our website, and we'll link that in the video below and in the description to the podcast where we discuss this further. The very first assumption of the central limit theorem is that you have a sequence of independent and identically distributed random variables. That is a very strong condition. Independent and identically distributed, drawn from the same probability distribution, and they are independent. Now, if you've been following our research, you know that it's actually not a very common thing for data to be completely independent. In fact, that otherwise we wouldn't be studying, probabilistic dependency. So if you don't meet that requirement, done, over, no more.
Don't read further on the theorem.
You're done. It doesn't break the theorem if you have a sequence of variables that's not independent. You're done. You didn't break it.
So why this is a peeve for me is because it's a misunderstanding of what a theorem actually is. A lot of work goes into making something a theorem. Because you can have a claim, you can have a proposition, you can have a conjecture, you can have a postulate, all these words that can be used for, this is an idea I have and I'm pretty sure it's true. But once you put theorem in front of something, once you say it is a theorem must come with proof.
And it must come with proof in the sense that we mean as mathematicians, not as, frankly, either scientists, which really they mean by proof, they mean strong evidence, or in law, where, again, they mean strong evidence. We mean proof, unbreakable logic.
And it takes a lot of work to do that. And you'll realize, if you go into making your own theorems, as we have.
A lot of work.
Yeah, a lot of work. And really, when all those conditions, that's because you figure out you can't get away with anything more. You know what I mean?
Right. So, as a slight tangent, to make a good theorem, the best theorems are the ones with the fewest conditions, right? okay, well, I need some laundry list of things for this to be true. Well, what if I take away one of these items? Is it still true? If not, it's a necessary condition.
Absolutely.
If I can take it away, well, then I don't need it. Take it away. So you want to whittle it down to the simplest, most general statement possible that renders the statement true. So the fewer conditions in the hypothesis, the stronger the theorem.
So it's not to say that somebody can't discover something, a mathematician can't make something, and then somebody can come along later and actually broaden the scope and say, you know what, you could have gotten away with this. Like if you can strike this condition and get more out of this theorem.
We actually have our own examples of that.
Yes, we do.
So the distributions we've generalized, the geometric, the negative binomial, the multinomial, the fact that we have generalized those distributions and have created a broader class of probability distributions does not render the original ones false. It simply means that you didn't have to be quite as restrictive as we thought.
And it's okay that you don't see all of that when you're first writing the theorem that you start with.
Right. I mean, even in my dissertation, one of the things that I wanted to prove was that a certain class of distributions would force a certain function shape for the efficiency of a server. And my intuition was strong, a class, a very general class that met some very general conditions was going to guarantee that my function in question would have a maximum. I still, to this day, even though it's been almost 3 years since I started proving that theorem, believe that it's true. And I have been able to break it down into different subclasses and then show the conditions under which it is true, but I have never proven that kind of unifying theorem I set out to do. And it's been 3 years and I'm still working on it. I think it's my turn to pick one. I'll pick a light one to start with. All right, so this one we can all identify with. Take a function, trig function maybe, sine, cosine, tangent, natural log, which isn't a trig function, but natural log.
These are functions, by the way.
When you see these written, and this is my peeve because, oh my God, math books do this too. Mm-hmm. If they're functions. Functions have arguments. So if you write cosine of theta, don't write cosine space theta. Put parentheses around it. Why? Functions have arguments. Let's say I want to, give my students an exam. And I wrote cosine space theta space plus space 5. Do I mean cosine of theta and that quantity plus 5? Or do I mean the quantity theta plus 5 and then you take the cosine of that quantity? Without the argument, those parentheses, it's ambiguous. It's completely ambiguous. Sometimes a book will be like, oh, I'll put an extra space there, and you're just supposed to interpret it. No, it's not obvious. The context is not obvious.
It's just going to get you into trouble.
It's going to get you into trouble, and it's bad enough when I see it in math books because it's cultivating bad habits, but it's going to be even worse if those habits are carried to, I don't know, somebody who works on the rockets from SpaceX, for example. And, oh, dang, guys, I meant cosine of theta plus 2, not cosine of theta, the quantity theta plus 2. I'm sorry. That's going to cost a couple million to fix, isn't it? These things have some serious potential consequences and repercussions. So there's my light one. Functions have arguments. Easy solution. Put parentheses around the argument of your function.
I guess while we're on the subject of light ones and things like that that get on my nerves, I have a few problems with symbols and way things that are typeset. I've seen quite a few things. Have you ever seen in a textbook they use the element sign but backwards for such that?
Not often.
It's not intuitive at all.
So what books have you seen that in?
Well, the interesting thing is it wasn't even like a really old book. It was a book on real analysis, and I can't remember what the title was, but it was a sort of compendium novel, one of those sort of where you put together 2 volumes of the same subject and you make it into a whole book. Not ours.
It's not one of ours?
No,
not in
we
our
don't.
library?
We don't have it. I saw it a long time ago, and it's very confusing.
And it stuck with you?
Definitely, because why is it a problem? If you want to define that symbol to mean that, that's fine, I guess. But if you're in the practice of using like the subset symbol and you reverse its direction to mean the same thing, like just in the other direction, like A subset B, and if you write B on the left and turn it around and make A to the right, then it still says A subset B. Well, then if you're using the backwards element sign, now it still reads like an element sign to me, just in another direction.
I've actually never seen that symbol, basically the reflection of that symbol used for such that. I've always seen, for me, I either see colons most often, right? X is a real number, colon, X is greater than 0. So X is a real number such that X is greater than 0.
That makes sense.
Or you'd see the vertical bar. Now, I don't like the vertical bar.
I don't either. It's way too many places.
The vertical bar, because I'm a probabilist, means condition on, given that, right? So the probability that X equals 5, given that Y equals 2.
And being that, probability is a measure, so you're taking, probability of sets, it could be very unclear as to what you mean.
So for me, what symbol would you prefer for such that? To me, I always use a colon.
Colon is good. It specifies and it carries over to language. It makes sense. It's intuitive. On that note, I guess sort of things that bug me about symbols, the backwards L for let, I think that's going too far.
Oh, you don't like that? Why not?
I just think that it looks silly.
It looks silly? Is it a purely aesthetic thing for you?
Yeah, kind of. And it's kind of like, the names of the months, when you abbreviate them, we don't do that for words that are 3 letters or less. Like, you don't need to do it for let. Exists, I kind of get.
Maybe I just want to be, purposely lofty and confusing.
Okay, well, if you are going to typeset a backwards L, make sure you do it in sans serif.
Have you seen a textbook where they use the backwards L and use a serif font for that?
No, but I can make it happen if I want to.
Yes, Jason can make anything in typography happen if he wants to. He can make anything in LaTeX happen if he wants to. I'm actually still impressed at some of the figures he's been able to generate in LaTeX simply by coding it in LaTeX.
You do call me the LaTeX whisperer.
Well, that's true, though. I mean, for anyone listening to this, especially if you're somebody who writes your papers or documents in LaTeX, everyone hates BibTeX. Everyone hates BibTeX.
Seriously, do you know anybody that sings its praises?
No. It's a necessary evil. It's a good way to keep track of your bibliography. But I swear, and I'm not crazy, the only way my bibliography ever compiles is if Jason is standing in the room.
Yeah, and this is, again, I'm only standing. It's not like I've made changes.
No, it's like he gives it the evil eye or something and it actually works for me. And I will not have changed a darn thing. Nothing. It just works for him. Same with compiling in Kelitech. It only works when you're looking at it.
I compile almost exclusively with Kelitech.
Why?
Because I like to change the fonts to what I like.
Well, I like changing the fonts too, but why can't you do that in the PDF LaTeX?
Because I want ones that aren't already set with their math support and stuff. I just make it difficult. I'm being difficult is all.
I mean, I like it too, but it means that you're going to have to stand in the room whenever you use really nice IMFL or Old Standard fonts.
Actually, I'm working on that, so we'll see what we can get with that.
All right, that's super convenient.
What's your heavy peeve?
Ooh, my heavy peeve. I have lots of heavy peeves, but in the interest of keeping this not to be a laundry list of me, bitching, it's actually one that came up on Twitter, and it was a mistake that I found in the calculus book. I'm currently an adjunct calculus instructor at Foothill College in Los Altos. And I appreciate calculus books that do try to tie, because calculus is everywhere. And I appreciate calculus books trying to tie the, I guess what you'd say the computational tedium that calculus can sometimes be to places that people would say, oh, they actually matter. Now, I care about calculus in general, but where they actually matter. Now, the one I used as an undergraduate had a lot of engineering examples. Why? Well, Georgia Tech assigned it. It's an engineering school. And the one that Foothill uses decided to tie double integration to probability, joint distributions of probability, which I think was fantastic. It's great. Calculus and probability are inherently linked. And it's good to kind of point that out in a different way than most stat books would try to. However, it made a fundamental error. It said the following, that if the probability of a certain event is 0, the event is impossible. And that is wrong. That is completely wrong. And it is a little bit complicated if we want to get really deep into it, and it's heavily measure theoretic. But we can actually have a fairly simple example. Let's say you want to draw a real number, somewhere from, 1 to 10. A real number, right? So you're talking about a continuous interval.
Mm-hmm. So pi and square root of 2 are in there.
Yep, pi square root of 2. Now, we can find and assume it's a uniform distribution, right? So the probability of anything is the same. Now, when it's a continuous interval, the probability of drawing its pi, for example, the probability of you actually drawing the number pi from that continuous interval is 0. Why? Because pi is itself has no weight, right? Probability is ultimately calculated essentially by, if it were a histogram, the length of the interval times the height, right? It's a box, it's a rectangle. Now just like in calculus, what do? When we make things continuous, we take that interval and we shrink it to 0. What's the weight of a point? Nothing.
Yeah, it has no width.
It has no width, right? So a line is one-dimensional, a square is two-dimensional, a cube is three-dimensional. A point has no measure, but yet you're drawing a point. Now, it is totally possible for me to draw the number pi out of that interval.
It's in there.
That event can happen. It is in the sample space, but the probability is 0. It is a little bit of a nuance in probability theory because most of what we think about in probability deals with discretizing.
Discretizing.
Making things discrete.
Okay.
Making things discrete, right? We deal with discrete things in the real world, right? Continuums, even in computation, don't really exist. We can't handle that. So we make everything discrete, but really, really tiny. Or lots of intervals or whatever. From an intuitive perspective, that's why it seems weird. You're used to a sample space being drawing balls out of an urn or picking a card, things that are discrete. You're not used to thinking about continuum and the fact that points in a continuum have no weight. So it seems a little bit strange to consider, but events with probability 0 does not mean they are impossible or cannot occur. Conversely, events with probability 1 are not certain. That is not guaranteed. The only thing that's guaranteed in probability is something that has already happened. So when we say probability 1, and this again gets into some measure theory for why we have to define it this way, is the notion of almost surely. Because if it is possible for an event with probability 0 to still occur, then it means that probability 1 cannot be a guarantee, right? So anyway, that's my heavy pet peeve. It was a difficult thing even to explain to my introductory stat students because to go really deep into this, I guess it's not even a philosophy, it's deep into a full understanding of what this means and why this is true and why this makes sense is a little bit heavy. But keeping in mind the simple example of a point on a continuum has no weight, yet you can draw a point, you can sample a point from a continuous interval. So the mathematical probability of that event happening is 0. However, it can still be done. So that's my heavy one. We have other ones, but we are going to try and cap it at 20 minutes, and just like our brain wrinkles, we try to make collections, and when we have another pile, then we'll do another episode. But what are some things we kind of have coming up in our calendar, just as some, company news?
No, we're attending the SNEA Symposium.
Oh, right. If you're headed to the SNEA Symposium in San Jose, January 22nd? The last week in January.
25th, I believe.
Yeah, the last week in January. If you're in San Jose, head to the SNEA Symposium, and we'll be kind of in and out of there. Registration is free, I believe. Mm-hmm. So catch us there. We do have stickers. I will be a delegate for the Tech Field Day, it's Tech Field Days, Storage Field Day 15, also in Silicon Valley, March 6th through 9th. So watch out, companies. The Math Citadel will be checking up on you. As always, you can get in touch with us several ways. You can go through our contact form at themathcitadel.com/contact. You can also reach us on Twitter, the official Twitter being @MathCitadel.
Yeah, if you want to talk to me, I'm @Jasonographer.
You can also reach me at @MathPocalypse on Twitter. And that's our second podcast for 2018.
So until next time, whenever we have another pile of math grievances or brain wrinkles, or we just thought about talking some more.
If you actually would like to be a guest on the show, or if you have an interesting discussion you want to have, we're willing to take applications for guests to be on the show. If you'd like one of us to come to your podcast and talk either business, math, Marvel movies, or whatever, just get in contact with us. And so, as Jason said, until next time, thanks for tuning in.